Hello everyone, I am Waad Almasri and I will be presenting you today my paper, GMCAD, an original synthetic dataset of 2D designs along their geometrical and mechanical conditions. I will first start by stating the motivation behind the creation of GMCAD, then go through a brief literature review. After, I will detail the consolidation of GMCAD, and finally end with concluding notes and the future works. Our work is in the field of design for additive manufacturing. In fact, traditionally, to manufacture a mechanical part, an engineer proceeds as follows. First, he defines the design specifications. Then, he launches a topology optimization, which suggests an optimal geometrical shapes in terms of material and functionality. Third, he recreates the CAD inspired by the proposed shape while considering implicitly the geometrical constraints of manufacturing. Finally, he tests the performance of the part and prints it. The problem with this process is that it is costly in time and performance, especially since first, the topology optimization is a method based on finite elements. In other terms, it is iterative and computationally expensive. Second of all, changing the geometrical shape of the design in order to comply with the manufacturing constraints can compromise the functionality of the part. Additionally, if the performance is degraded to an unacceptable level, we have to redraw the shape, rerun the performance analysis, and get stuck in this loop. Last but not least, the manufacturing constraints themselves are not yet formalized. They are varied and contradictory between processes. Some even still lack an exact mathematical description, like hanging features, which makes it further challenging to integrate them at the conceptual level of design. Therefore, in our work, we choose to explore deep learning techniques at the second phase in order to accelerate the design for additive manufacturing process and avoid getting stuck between the third and fourth phase. More precisely, we ought to explore generative methods to integrate manufacturing constraints into the mechanical design at the conceptual level. However, one major issue to our approach is that we need a dataset of designs with mechanical and geometrical constraints. In the literature, one can find topology optimization codes from which one can generate from input mechanical constraints 2D or 3D designs or CAD designs from which one can extract geometrical information only. Consequently, since for our work we will need both information, mechanical and geometrical, we have decided to create a dataset with 2D designs alongside their mechanical and geometrical constraints, GMCAD. In order to accelerate design for additive manufacturing, researchers have proposed two approaches. The first approach is to integrate manufacturing constraints directly to the traditional topology optimization methods. The manufacturing constraints considered are mainly the build orientation and the overhang constraint. And this is due to the fact that these constraints are the most general in manufacturing. The second part chose to instead explore machine and deep learning to either partially or totally replace finite element topology optimization methods. However, none of these methods have integrated manufacturing constraints, but they have left them to the reinterpretation phase. And for the methods incorporating manufacturing constraints, well, the authors reported convergence problems. Their methods converged to solutions 1 time out of 10. Also, not all manufacturing constraints can be formulated analytically in order to be integrated to topology optimization methods. Thus, what we propose is to explore deep learning in order not only accelerate topology optimization, but also be able to integrate manufacturing constraints at the conceptual level of mechanical design and be able to accelerate the whole design for additive manufacturing process. In other words, have the best of both worlds. However, for our approach to work, we need a dataset of designs with mechanical and geometrical constraints altogether. And as we have mentioned previously in the literature, such dataset does not exist. Consequently, in this work, we have decided to create it. In this slide, we show the global roadmap we follow in order to create this deep learning additive manufacturing driven topology optimization model that will integrate mechanical and geometrical AM-related constraints. This work is divided into two big parts. The first part makes the subject of this article, which is the consolidation of GMCAD, and the second part will be submitted soon in another conference. The consolidation of GMCAD consists of 4 steps. Step 1, the creation of a dataset of designs with their mechanical constraints from an open source topology optimization code, SIMP. It's a solid isotropic material with panelization, a density-based topology optimization method. And this data set is called DB1. Step 2, train deep learning models to predict the mechanical conditions like boundary conditions and load using DB1. Step 3, generate CADs with precise geometrical constraints. Their shapes definitely were inspired from the ones generated by topology optimization SIMP. We call this dataset DB2. These CADs are after that converted to images with filtering techniques and point clouds. Step 4, predict the mechanical conditions of these CADs using deep learning model trained in step 2. So in other terms, it's DB2, that is, we're gonna predict the mechanical conditions of the designs in DB2 and get GMCAD, which is a data set of 2D designs alongside their mechanical and geometrical constraint. And after that, we can go to the second part and train DL-AMTO. In the next slide, I will further detail every step. Now, for the step 1, to generate DB1, we have sampled the mechanical constraints using the following strategies. We chose one type of boundary conditions, encastrated ones, such that the number of encastrated nodes follows a Poisson distribution of lambda equal 50. Also, we generate designs subject to only one load with an orientation following a uniform distribution between 0 and 180 degrees. Finally, the volume fraction was sampled from a normal distribution of the mean of 0.3 and a standard deviation of 0.05. The volume fraction is actually the percentage of material, of final material we would like to have it left in the volume. Like as you can see here, like if we average the density material here, we'll have like, I don't know, 0.3 or the value it is. This data set consists of about 6,000 2D designs of dimension 100 times 100 and their mechanical constraints. We have separated them into a train and a test set in order to train and evaluate the mechanical conditions predictors and step 2. Here is a sample of 2D designs with their mechanical constraints. In red, it's the boundary conditions, and in green is the load location with its orientation. Now, step 2, the mechanical conditions prediction. Well, the mechanical conditions are 3, the volume fraction, the boundary conditions, and the loads. For the volume fraction, it's simply the average of pixels in the design, the average density. However, for the boundary conditions, well, they are 2D matrices of dimension and x plus 1 and y plus 1 for a design of dimension and x and y. And with null values everywhere except for the fixed nodes which are set to 1. And for our case, BCX and BCY are exactly similar because we have the type encastrated. In order to predict these matrices, we use the boundary deep learning predictor, which is a convolutional neural network. For the loads, however, they are also 2D matrices with the same dimension as the boundary conditions one, with null values everywhere except for the loaded node, which is set to the orientation 45 degrees here, for example. In order to predict the load matrices, we actually use 2 convolutional neural networks, the forced deep learning locator and the forced deep learning angle estimator. For our work, the dimension of the design is 100 times 100. The boundary condition deep learning predictor is a convolutional ResNet model that takes the 2D design as input and outputs a 2-channel 2D matrix corresponding to the boundary conditions along the x and y axis. Now for the forced deep learning predictor, well, as we have said before, the load matrix is a sparse matrix with null zeros everywhere except the loaded node. And this value, this non-null value, has a wide range of values from 0 to 180 degrees. We set it from 5 to 180 degrees in order not to confuse the 0, because 0 is equal to the absence of load. Consequently, predicting the load matrix is a very challenging task. Hence, we separate the load location prediction from the load orientation one. The load location is predicted by the forced deep learning locator. However, for the load orientation, what we do is, first of all, we augment the load matrix by a filtering technique, like here. After that, we reduce the dimensionality of this matrix and by selecting only circumference nodes. Why? Because we only sample loads from the edge of the domain space. We end up with a 1D vector corresponding to the load orientation. This 1D vector is predicted via the forced deep learning angle estimator. Now both models, the locator and the angle estimator, they take as input the design and the boundary conditions and outputs the location, and for the second one it outputs the 1D augmented vector of the load orientation, which is after that reshaped as a 2D matrix, and the final load matrix is the product of these two matrices, the one of the location and the one of the orientation. In this slide, we show the performance of the mechanical conditions prediction. Well, as you can see, in order to evaluate the mechanical condition predictors, we computed three metrics: the difference between the true and predicted boundary condition nodes, the difference between the true and predicted load nodes, and the difference between the true and predicted load orientation. And as you can clearly see, the boundary conditions and force locations are well predicted. However, for the angle estimations, well, they need to be enhanced because sometimes the load orientations can be a little bit divergent, like in those three examples. Now, for the step 3, which is the generation of DB2, well, the CAD designs were inspired from the SIMP ones, and were drawn using PyGmesh. It's a Python library to draw CADs. We scripted the CADs. In fact, we define a 2D CAD as a collection of connected beams such that every beam is a rectangle of 4 coordinates. In fact, this definition makes it easier for us to extract several geometrical information like thicknesses, length, and angles. And to be more precise, the PyGmesh script actually generates a .vtk file. Then we convert this VTK file into an image, a .png file, with filtering techniques on point clouds, as you can see in the example here. Because why do we need the image-like files? Because when we want to predict the mechanical conditions over DB2, we need to use the deep learning mechanical conditions predictor, which take as input images. Here I show you a sample of DB2. The first design is the SIMP one. This is like, and the other designs are inspired from this shape with different geometrical constraints: minimum length, beam length, minimum maximum thicknesses, minimum overhang, and the number of elements. I'd like to point out here that the overhang is the angle between the build orientation, which is here the y-axis, the pink vector, and the normal of every beam in the design, and after that we choose the minimum one. So the normal of every beam. Now for the last step, which is the inception of GMCAD. Well, GMCAD is created by predicting over DB2 the mechanical conditions. Until the submission of this article, we had generated about 36,000 designs, and here we show the distribution of some geometrical and mechanical variables like the load orientation, the number of boundary condition nodes, the minimum maximum thicknesses, minimum maximum length, number of elements. Like we have designs from 3 to 12 bars. We have minimum overhang that goes from 0 to 60 degrees, or load orientation from 0 to 180, etc. Here from this figure, what I would like here also definitely this is GMCAD finally. We have the design with the boundary conditions, as you can see, and the geometrical constraints. But from this figure, what I would like to point out is that we can see that simply changing one geometrical condition, it can trigger a big difference in the performance of the design. Here, the mechanical performance is measured with the compliance in joules. It's the energy of deformation. In the first example, for example, in red, the performance deteriorated after changing the thickness of the bars. However, in the other case, adding an element, adding this bar, well, improved the mechanical performance twice. Therefore, the mechanical performance of a design is sensitive to a very minor geometrical change, and obtaining an optimal design respecting all constraints requires several geometrical modifications. And with the old mechanical design process, this required repeated drawing and performance testing. The goal behind the LAMTO and subsequently behind the creation of GMCAD is to speed up this step, because in our case, the geometric shape outputted by the LAMTO will already be complying with both constraints, mechanical and geometric. To conclude, in this work, there is a synthetic public open source dataset of 2D designs alongside their mechanical and geometrical conditions is consolidated, GMCAD. You can find it on our GitHub repository. GMCAD bridges the gap between the mechanical and geometrical world in the design for additive manufacturing. And in our previous work, we have proved that deep learning allows to consider geometrical aspects in design for additive manufacturing. In this work, we only considered the number of elements as the number of bars as a geometrical constraint. You can test our model, our previous version of the model at this application. It's an application online where you can actually compare finite element topology optimization with deep learning 1 with the playing just selecting mechanical constraints and the number of bars and generating designs with their mechanical definitely evaluation. In the future, GMCAD will be augmented all along the way. There is a platform that is currently being in progress in order to facilitate the sharing and the collaboration between research community. Additional variables can be added like mechanical constraints like nonlinearities, thermal distortion, etc. Also the GMCAD image-like designs, they could be further improved with computer vision techniques and filtering techniques in order to ensure that they are geometrically valid and that the connectivity is ensured. Currently, a deep learning additive manufacturing driven topology optimization is being trained with GMCAD to improve our first version with further complex geometrical constraints like thicknesses and length and overhang. GMCAD will drive definitely deep learning multi-objective controllable design generation techniques that can be implemented into a CAD software as a lighter and faster generative design module. Thank you.